Hello everyone, my name is Prajwal B. Saunshi. I am currently pursuing my Bachelor's of Engineering in Electronics and Communication Engineering at AMC Engineering College, Bengaluru, and I have successfully completed my embedded internship at Emertxe Information Technology. During this internship, I have worked on EV ADAS dashboard using STM32 and the Python. It's a real-time electric vehicle monitoring and the advanced driver assistance system. Today I will explain the complete project including the architecture implementation phases and the embedded programming, ADAS features and the final dashboard demonstration. The main objective of this project is in real time and improve the driver safety using the advanced driver assistance systems or ADAS. The project combines the STM32 Bluepill microcontroller, Python dashboard, ultrasonic sensors, UART communication and Pixim lab simulation. The dashboard is continuously display the important vehicle parameters. This project demonstration how the embedded systems and Python visualization can work together in the modern electric vehicles. Then we go to here we can see the challenges. The modern electric vehicle generates the huge amount of sensors data every second. As we know, without centralized monitor system, becomes difficult for the drivers or engineers to monitor every parameters. For example, battery conditions, vehicle speeds, motor temperatures, blind spot and collision risks. As there is no monitored properly, they may cause us accident or vehicle failures. Solution for this is real-time Python dashboards, which we decide a real-time live monitoring and ADAS detections, fault altering, live dashboards and tried alarms and drive modes. This makes the vehicle safer and easier to monitor. The systems architectures and the overviews. The four stages data pipelines. First is sensor stage, which will get the inputs from the physical environments. The simulated sensor feeds the STM32 Bluepill, then which will process the EV dynamics and the ADAS logics. Then the transmitted telemetry over the UART to live. The data flows from sensors to STM32 Bluepill, EV, ADAS engines and UART serials. Then it will goes to Python, parcels and the Matplotlib dashboards. We are using 115200 bureau rates. Next slide. Industrial mapping. This slide compares our projects with the real electric vehicles. In real electric vehicles, sensor measures the wheel speeds and the distance, ECUs controls and the vehicle's functions and the CAN bus transfer data. CAN means controlled area network, and the lastly it will be shown on the instrument cluster display information. In our project we are using potentiometer simulate the sensors, and STM32 Bluepill acts as the ECUs, and the UART will replace the CAN communication. UART means universal asynchronous receivers and transmitters. Python dashboards acts as the vehicle instrument cluster. Although simplified, our project follows the same working principle used in the real automotive systems. As we are having the project roadmaps, the project is completed in these phases. The phase includes the environmental setups like STM32, Spixim Labs, and the Python setups, GPIO and their peripherals, general purpose input and outputs like LED, PWM buzzers, timers, 1, 3, 4, and the analog to digital sensor inputs, acceleration, brake, and motor temperature, and EV dynamic models like speed, torque, state of charge, range, and regenerative braking. This regenerative brake works when we apply the brake, the SOC and the range increases. State of the charge increases and the range also increases. If the state of the charge increases, then the range is automatically increases. The driver moves. And here comes with the ultrasonic sensors. This plays the major role in bird eye view. We are using HCS of O4 sensors left, right, and front for blind spot, time to collision, and forward collision. In phase 6, this comes with the fault and alarm systems. Like we are having 4 levels of alarm priority and UART telemetry, speed, SOC, torque, temperature, and range. UART shells, live parameter injection via serial commands. Now we come with the environmental setups and GPIO peripherals. The goal is the working STM32 firmwares with the LED buzzers and timer interrupts forming and foundation for all downstream modules. Here comes with the STM32QID for firmware programming and the Pixim lab for hardware simulation and the Python 3+5 dashboard and the library and the Matplotlib and the NumPy for live visualization and the PySerial for UART communications. Here's with the we configure the peripherals. Next, the timer 1 updates the calculation every 10 milliseconds. Timer 3 reads the sensors every 100 milliseconds. Timer 2 measures the ultrasonic echo timings. Timer 4 generates the PWM for buzzers. Analog to digital channel reads the acceleration pedal, brake pedal, and the motor temperatures. The GPIO pin controls the LED for collision warning, blind spot detections, and the system faults. UART 1 provides the communication between the STM32 and the Python. Then we come with the next slide. Analog to digital sensor systems and the EV dynamics. Here the STM32 reads the analog sensor values. The ADC converts the analog voltage into digital value. These value represents the acceleration, braking positions, and the motor temperature. Usually these inputs, the EV dynamic module calculates the motor torque based on the acceleration, pedal positions, and the driver. Vehicle speed is calculated using simplified vehicle dynamic equations. And the battery state of charge reduces gradually depending upon the power consumption. Driver range estimated based on the battery capacity. The driver modes eco, normal, and sport. We have not implemented that eco, normal, sport. We have implemented in normal state. Each mode changes available motor torque. Regenerative brake. When the brake is applied while moving, the motor generates the negative torque and regenerates the battery slightly. This closely resembles regenerative braking used in the modern electric vehicle. As you can see the bird eye sensor layout. This is the one of the most important part of the project. We use the 3 HCR SO4 sensors. One sensor detects the obstacles in the front and the 2 sensors monitors from the left and the right blind spot. These implements the advanced driver assistant features includes forward collision, time to collision and blind spot. Forward collision. If an object is detected, a warning is generated. If it comes below 20 centimeters, a critical alert is generated. The system estimates how quickly the vehicle will reach the obstacles. When the time to collision will estimates how quickly the vehicle will reach the obstacles. And the blind spot detection. When an object is detected within the 40 centimeters, within the 40 centimeters, while the vehicle is in above 20 kilometers, then the blind spot warning is activated. The park assistant is at low speed. All the three sensors calculate the parking scores. Then here comes with the overspeed advisory. It fires when the speed is exceeded 120 kilometers per hour. It is only fires when the speed is exceeded 120 kilometers per hour. Then we can go with the project also includes the fault monitoring systems. The different faults are stored in the different fault registers. For example, the high motor temperature, low battery, SOC, collision, ultrasonic sensor failures, and the UART communication failures. The alarm systems also have four levels. The level 0 is normal operation, no alert actives. And the level 1 is advisory, blind spot or vehicle over 120 kilometers. Here comes with the critical. Critical occurs when the vehicle speed when the vehicle is below 20 centimeters from a vehicle, or time to collision is less than 1.15 seconds, or dashboard flashes red color. The STM32 continuously sends two serial data frames every 100 milliseconds. The first frame contains the speed, SOC, torque, temperature, ranges, and acceleration brake. And the second frame contains front ultrasonic sensor, left ultrasonic sensor, right ultrasonic sensor, and time to collision, collisions, blind spot detections, alarms, and fault status. It is fault status is shown in the hexadecimal or hexa. This is the field for references. Speed, ranges, and the time to collisions, acceleration positions, state of charge, torque, brake, and blind spot detection, alarm, priorities, and front, left, right, ultrasonic sensors, temperatures, and the fault byte in hexa. Here completes with my presentation of this project. Then we can go with the demo. There I will explain how this all will work, this all field reference will work, and I have implemented this successfully in STM32, Bluepill, Pixim Lab, and STM Cube IDE, and Python dashboard. Here here is the configuration of the STM32. Here this pin, I had configured these pins, and these are all the header files which have included. These are the source files which I have included, and we have three timers: timer 1, timer 2, timer 3, and UART 1 for UART communication. We have used 115200 bureau rates, and these are the general purpose input and output pins which I have configured for the ultrasonics and other components. This is the main.c file. And this we have included this all EV underscore control dot h, ultrasonic dot h, ADAS dot h, fault dot h, UART shell dot h, and buzzer dot h file. This file contains the working codes. And now we can build the project. The project is built successfully with the zero warnings and error. You have seen before that this configuration. I think this is the timer layouts. I have load the file before only, so if you want to load the bin, you can go just load here. This is the file I have made, and then we can open. I have already opened the file. Then we can go to module spares. Here we can go. Because why the alarm has came means the see, you can see here that I have configured all this. Why this sensor is buzzering means the front sensor becomes very near, front distance becomes very near. If I increase the distance of the vehicle in front, then the alarm has deactivated. I will explain this virtual terminal with the Python dashboard. Now the speed is increasing rapidly. You can see if I increase the speed is increasing. The speed is increasing from 7.7, 8.5. The speed is increasing rapidly, as we can see here on EV dashboard. The speed is increasing rapidly. As the speed increases, the battery will drain, and the ranges also become decreasing. Here 3281 kilometers becomes 3277 kilometers, and the mode is in normal mode. And this is the graph of the speed, and this is the speedometer, and this is the bird eye structure view. I will explain later that the collision, time to collision rates, and this is the EV metrics table. As we can see, this is here is the alarm status. Now I had explained this. Now I will show the braking, regenerative braking, how it will work. As we can go here, this is the brake pedal. As we can decrease the acceleration, as we increase the braking, see here we can see the braking is 94% and the acceleration is 2%. As we increase the braking, the speed is decreasing. See, from 20.5 to 20 becomes. Then as the speed decreases, the SOC is increasing. The speed and the SOC is inversely proportional. Why it is SOC is increasing? Because the torque becomes negative. So the SOC is increasing. As the SOC is directly proportional to the range. As the SOC increases, the range is also increasing. See, brake is applied and this is the maximum range the vehicle can provide. See, now the brake is decreased. So for fault detection, see, we can reduce the brake. Here we can see the status. The speedometer becomes 14 and this is the maximum ranges of the vehicle and it is increasing little and the brake is 99% and the graph becomes decreasing. Now we can see the faults. If I increase the temperature of the motor, then the fault occurs. See, we can see the alarm advisory. We can open the virtual terminal. Here we open the virtual terminal, then we can see the fault and the buzzer is turned on. We can see here the motor temperature has increased. In dashboard also it is visible. The motor temperature is 106.8 degrees Celsius and the fault is occurred in hexa. Now you can see, if I decrease the distance between the vehicle, first it is the now you can see the warning, because the time to collision is 2.6 seconds and the speed is 2 kilometers per hour. The speed I had increased the brake pedal, so the speed becomes 2 and the vehicle is in the normal state. See, no buzzer. If the vehicle becomes more near to the alert plus warning also becomes and the dashboard becomes blinking. It's very near to it. The time to collision will update. It will become 0 and it is in critical situation. As we increases, it is deactivated all the alarms. As for to detect the left and right sensor, the acceleration pedal must be increases and the brake must be decreased, because the speed should be above 20 kilometers per hour. Below 20 km speed, the blind spot is not detected. See here in virtual terminal. See, the speed is increasing. We should wait for. Okay, now you can see here it's become 17.5. If I decreases also blind spot is not detected. When the vehicle speed becomes above 20, then see you can see here 20.2, the vehicle speed increased and the alarm has activated. For this also same, if it becomes, let's see here, green up, green like LED is turned on for right sensor. Now you can see on the Python dashboard. See on the bird eye view, you can see that both the blind spots are detected on left and right, and the alarm is advisory, and the acceleration is 100%. The vehicle is increasing, and the range is also decreasing because I had increased the acceleration pedal. And here graph we can show from brake pedal to acceleration pedal. If the speed increases above 120 kilometers per hour, then the vehicle will show advisory. I will show that also. As you can see here that the speed is increasing rapidly. If the speed exceeds 120 degree, then the advisory alarm will activate. See here the speed is increasing rapidly, and in the bird eye view there is no blind spots are detected, and the front vehicle is far away from the our vehicle. As the speed is increasing, the range is decreasing, and the battery is also draining. As you can see here that the speedometer is increasing. See, from 120 to what changes to, it is increasing from 120 to 122. Then the advisory alarm is activated. See, as you see here the range is also decreased to half, and the state of charge is also decreased. As we can see the advisory alarm, it is exceeding the speed. This completes the project implementation and the demo. Here, this project helped me to understand how the embedded systems are used in the modern electric vehicles and the ADAS applications. Thank you for giving these opportunities.